Good evening, everyone, and welcome to session number 7 of the Amateur Radio Technician class. So this is where we are in respect of the topics that we need to cover. We are towards the end of the radio wave characteristics section. Last class, we looked at the following. We looked at wavelength, the difference between HF, VHF, and UHF. We looked at the meaning of RF, what the ionosphere was, the concept of line of sight, the radio horizon. We discussed multipath distortion. We looked at the concept of knife edge diffraction. We also discussed what picket fencing is. We looked at the effects of vegetation, and we ended up on page 28 of the No Nonsense Guide, which is the book that we are utilizing for this course. So I would like to thank June for providing a link to radio stations globally. So that website that you see there, radio.garden/live, you can listen to any broadcast radio station globally. It's a very nice website. So again, thanks June for the suggestion. Also, all of the course material, including slides, books, and reference material, including part 97, as well as the question pool, can be found at the link below. So again, these slides will be shared via email, so you can get that link. It may be difficult to copy it now, so it will be in your slide deck should you not have all of the documents, and that location will be updated as we add new material for you. So we had discussed the concept of the relationship between frequency and wavelength, and we looked at this formula where frequency is equal to 300 over the wavelength, and if we move the terms around, we get wavelength is equal to 300 over frequency. All right, but last class we looked at a calculation, and we just wanted to go through that calculation a little more in detail so that we could understand when someone says we are in the 2-meter band, what that means, or if we have a frequency, we could determine what meter band it is. So the question that was asked in the question pool really was about the 2-meter band, and we said that the 2-meter band was 144 to 148. But how do we actually know when we say 2-meter band, what frequency range we are referring to? So let's look at that. So remember, we have the formula frequency is equal to 300 over the wavelength. So if the wavelength is 2 meters, we simply plug 2 into the formula where we have wavelength. Remember, this is the symbol lambda, that means wavelength. So 2 meters is the wavelength. So we plug 2 into the formula and we get F frequency is equal to 300 over 2, or 300 divided by 2. And that is simply 150. So the actual frequency is 150 megahertz. But on the right-hand side here, we have some of the amateur radio frequencies or spectrum or amateur radio bands. 1.8 megahertz to 2.0 megahertz, 3.5 megahertz to 4.0 megahertz, etc., etc., etc. But if we look to see which of the amateur radio bands that are allocated to hams to use is closest to 150 megahertz, we see that 150 megahertz is closest to 144 to 148. So that is how we know the 144 to 148 megahertz band is the 2-meter band. All right, so just thought we should demonstrate how we go from the meter band to the frequency. So this should look familiar from the previous slide. We had this table here that showed the amateur frequencies. And if you are licensed in Trinidad and Tobago, you will see these frequencies or something similar on your amateur radio license. But this information is put here as a sort of comparison. So you can see the amateur radio frequencies, it's given in megahertz, all right? And the wavelength. So you may observe a relationship as the frequency increases. This is 1.8 megahertz, 3.5 megahertz, 10 megahertz, 28 megahertz, 50 megahertz, 1,250 megahertz. So we are increasing the frequencies as we go down the table, but we will also notice that the wavelength is getting shorter and shorter. And that goes back to the relationship that we had before, where there's an inverse relationship between frequency and wavelength. In other words, when one goes up, the other one goes down. So this table just illustrates that for us very nicely. And these are the actual frequency bands or the spectrum that amateur radio operators utilize. So when we say we are on the 2-meter band, it means we are on the 144 to 148 megahertz spectrum. And just to understand where we are, to use the FM radio band that we tune into, 95.1 FM is between these two amateur radio bands. So this amateur radio band starts at 50, ends at 54. And the next amateur radio allocation is 144 to 148. So 95.1 is somewhere inside of here between these two bands. So the FM broadcast band is between these two amateur radio bands. Also, last time we talked about the difference between HF, VHF, and UHF. So these frequencies here, or these wavelengths, are in the HF part of the spectrum, because remember we said that HF is between 3 and 30 megahertz. We also said that VHF was between 30 megahertz and 300. And we also said UHF was between 300 and 3,000 megahertz, or 3 gigahertz. So this just gives you an idea of the various amateur allocations and the wavelength as to whether it's in the UHF, VHF, and HF bands. You will see why this is important, because as we go through the question pool, you may need to refer back to this chart to see why we are saying, for example, that the 2-meter band is VHF, all right? Or the 6-meter band is VHF. So that's why this table is here for you as a good reference. When we go through the question pool and we go to the questions, I'll mention this table so that you can go back and look at it and convince yourself. When we say the 2-meter and the 6-meter band is in the VHF spectrum, it's illustrated here, and you can also see what the frequency is. These arrows just simply illustrate what we talked about, which is as you go up or you go down this way, you're increasing the frequency, but as you go up, you are increasing the wavelength. A concept that will be discussed as we go through the question pool questions is that of antenna polarization. So on your screen, you'll see two antennas. This antenna, this could be you. This antenna could be another radio operator, and you all are communicating. So you have two antennas in use, yourself, the sender, and the other person, the receiver. But notice the orientation of the antennas. They are vertical, or top to bottom, vertical. And when antennas are vertical, because the electric field that is emanated when you apply a radio frequency to the antenna, the electric field is perpendicular to the Earth's surface. So because these two antennas that we are looking at here are oriented in this way, they are considered to be vertically polarized. If we were to look to our right, the top right, we will see, again, two antennas, but they are now horizontally polarized. They are flat with respect to the Earth's surface. So the electric field is not perpendicular anymore to the Earth's surface, right? But notice these two antennas are both, sorry about this, there's an error on the slide. This should have said horizontally polarized, so we'll correct it. So apologies for the this typo here. This is horizontally polarized. So these two antennas are horizontally polarized, and therefore they're in the same orientation. Now, if we were to look back at the left-hand side here, when we have antennas that are vertically polarized like this, you get maximum transfer of energy from one antenna to the next, right? When we have both of them horizontally polarized like this, we also have maximum transfer of energy. So you have maximum signal, all right? But let's look at the bottom part of the screen here, where this is vertically polarized, the antenna here, and the other antenna is horizontally polarized. The problem here is if I transmit using this vertically polarized antenna, and the person receiving me has their antenna horizontally polarized, 90 degrees, the signal received here will be very low because they are not using the same polarization. So as radio operators who are already using radios, it's useful to know that repeaters, for instance, their antennas are typically vertically polarized. So if you are using a walkie-talkie or handheld radio, and you hold the walkie-talkie like you would use a phone at an angle, you are doing almost like this. You are having your antenna horizontally polarized, and your repeater is vertically polarized, so you'll have a poor signal going to the repeater. So for maximum transfer of the energy or maximum transfer of the radio signal, you want the both antennas to be in similar polarity or similar polarization. So this should give us a little idea as to how we can improve our signals for maximum transfer. So just take note that when we say polarization or horizontal polarization, we are referring to the electric field associated with the radio frequency. Remember, radio frequency has both an electric field and a magnetic field. That's why it's electromagnetic energy, right? So when we talk polarization, we are talking about the electric field. Again, that will become important in the question pool. And this slide here, not that you have to learn anything off of it, but you know, we like to give something extra in the class. So these are some of the different types of polarizations that you will encounter in the radio world. You have horizontal polarization, where it's horizontal this way. Vertical polarization, so the signal is vertical. So if you can look at the perspective, it's vertical. And then you have dual polarization, cross polarization. You even have circular polarization. And even with circular polarization, you have right-hand circular and you have left-hand circular. This is really just reference. None of this really is extremely important to your course, but this is a little bit of extra material and relevant to your question pool. The point we make is that hams, we love to bounce signals off. All right. So we talked last class about the ionosphere and the various ionosphere. So we, as hams, love to bounce signals off of the ionosphere. But technically speaking, what the signal as it leaves your transmitter, right? You have a ground wave, also have a sky wave that goes up into the sky until it meets the ionosphere, a charged layer. And this signal will bounce off, or they tend to bounce off the ionosphere depending on the frequency of our transmission. But just to point out, that bounce is really the signal being refracted. All right, so you notice it looks kind of curved in the illustration here, but it's bending, bending, bending. So that is the concept of refraction. All right, so you have the ground wave and you have the sky wave. This diagram you saw last time, but just to re-emphasize the point that the horizon for radio frequencies is a little longer than for optical line of sight. You may be only able to see this point on the Earth here, but your radio wave will see beyond that due to the Earth's surface and radio waves sort of bending associated with that. It's called, again, refraction. Also, again, hams like to bounce signals. So we have signals bouncing off of the ionosphere as well. Again, another diagram you saw last class. We just emphasizing here that hams like to bounce signals, but we bouncing signals off of the ionosphere. All right. Again, hams, we love to bounce signals. So apart from the ionosphere that we're bouncing the signals off of, we have different layers of the ionosphere. So we have the D layer, the E layer, and the F layer. So we saw that the last time. But there is something on the E layer that appears from time to time. Hence the term, the word is sporadic. So from time to time, you can have a propagation where your radio transmission, your radio wave will go up to the E layer in the ionosphere and bounce. But that could be short-lived. The signal could be there for a short moment and disappear the next. So that layer is in the E layer, but it's considered sporadic E because it's intermittent and from time to time. And that bouncing, when you hear that signal, you might hear a fluttering of that transmission because it's sporadic or intermittent. Again, hams like to bounce signals. So what else do we bounce signals off of? So this is the Earth's surface here, and as a ham operator, we are on the Earth's surface with our radio, whether our handheld, mobile, or base station. And we would like to bounce signals off of things. But there are quite a lot of things that we can bounce our signals off of. For instance, we can bounce our signals off of meteors. And when we do that, it's called meteor scatter. So I'm transmitting, it bounces off of the meteors, and someone else on the other part of the Earth's surface will hear my signal because it has bounced off the meteors. All right. Also, you may have heard the auroras, northern lights, sometimes it's called. You can also bounce signals off of those northern lights or the auroras, aurora borealis in the north and aurora australis in the southern hemisphere. So you can actually bounce signals off of auroras. Again, that's why we say hams like to bounce signals. Another thing that we do as well, we take advantage of the fact that in the atmosphere you have cold air and warm air and cold air and so on. This is called temperature inversion when you have that warm air, cold air. And we send signals into the atmosphere, and when we do that, the signals scatter based on that temperature inversion, and we call that tropo, or more correctly, tropospheric scatter. Pretty long word, but we abbreviate it as tropo or tropo, T-R-O-P-O, but it's really tropospheric scatter. Now, when we do that scattering over a long distance, so for instance, on this side here, we'll notice that you have the cold air, warm air, cold air, so you have temperature inversion, and you have the scattering of the signal taking place, and it's bouncing and it's scattering and bouncing and scattering. When it does this, this is called tropospheric ducting. So it's a long range scatter, and you can have a transmission that would otherwise not be possible by using this concept of tropospheric scatter or tropospheric ducting. Also, the question is, does rain and snow and precipitation really of all forms, does that affect radio signals? Well, yes and no. It depends on the frequency of your transmission. But note that at frequencies in the microwave range, the microwave range is considered any frequency above 1 gigahertz, all right? But anything above 11 gigahertz is very much affected by any kind of precipitation or rainfall. Once you have rain and you're transmitting on a frequency in the microwave part of the spectrum or the microwave band, you'll notice this is a graph showing attenuation, which is reduction in signal. So note that radio signals are attenuated in the microwave part of the bands by rain and generally any form of precipitation. Well, we talked a bit about the ionosphere and the fact that we bounce signals off of the ionosphere. But we also saw in a previous diagram that the sun and the presence of the sun causes layers to exist or disappear depending on whether it's day or night. But there's also another phenomenon that we need to pay attention to as amateur radio operators, and that is called the sunspot cycle. It's an 11-year cycle that exists, and from this graph we see here, it starts in 1913 and it goes to all the way extrapolated or forecasted for up to 2031. So we're about here, 2020. So the red and blue lines show forecasts, and the gray lines show the actual. So this sort of gray line here is where the number of sunspots. So this y-axis shows the number of sunspots, and this x-axis is the year. So let's say this is 2019. Notice it's a low part of the sunspot cycle. All right, so you could look at the trend here. It's low, it goes high, it goes low, it goes high, it goes low, it goes high, etc., etc. And all the way here, 2003, you see here, it goes low, then it goes high, and then go towards 2019, notice it's very low. So right now, we're in a sunspot minimum where the sunspots are low, and that is not very good for amateur HF. All right, it makes propagation very difficult. Yes, good evening to you, Eric, and good evening, who is this? Looks like Colin. Good evening, Charlene, thank you very much. Just looking at the chat box. All right, so we need to be aware of the sunspot cycle, because when there are many sunspots, that causes HF propagation or HF radio waves to, it makes communications a lot easier, or it allows for communication to take place. When the sunspots are low, it makes radio communication, especially in the HF spectrum, very difficult. So pay attention to where we are in the sunspot cycle. All right, so we also need to be aware as hams that the different parts of the bands are very effective at different times of the day or night. And that is one of the reasons as hams, we need to be trained. We also experiment to see what frequency works well in the day and what frequency works well in the night. So all of this is just to show that during the night time, all right, the lower frequencies, which are these frequencies here, 160 meters, 80 meters, and so on, work very well in the night time. But during the daytime, the higher of the frequencies, all right, and these are basically HF frequencies, right? So when we say high, just bear in mind that this is HF that we're talking about. This is not VHF or UHF. This is HF frequencies. So during the daytime, the higher frequencies work better. And that is simply because of the ionosphere being energized. During the daytime, notice the layers in the ionosphere that exist. You have the D layer, the E, and the F layer is split into two. During the nighttime, notice we're not seeing any D layer here, but there's the E layer and the F layer becomes one. So why that affects propagation? Remember, the signal from the Earth goes and bounces off of the ionosphere and goes and bounces back to the Earth and skips and so on, right? Depending on the height of these layers, that will determine how well or how far those signals bounce, as well as the maximum usable frequency that you could use during day or night. So we need to be aware that depending on the day or night, whether it's day or night, the use of the frequency is important. You have to select the frequency to ensure that your transmission goes through. If you use the wrong frequency, your signal is going nowhere. All right. Again, we're coming back. So you notice all of these diagrams, they have a theme, right? You have the Earth's surface, and then you have, the ionosphere. And you see a signal that is leaving the Earth, going to the ionosphere, bouncing or refracting back to Earth, skipping and bouncing again and reaching another part of the Earth. That is how hams operate. That is why amateur radio equipment can be used to communicate without cellular towers and repeaters and so on. Hams can communicate from one part of the Earth to the other part of the Earth by bouncing the signals. What did we say? Hams love to bounce signals. But when these signals bounce, to get to the destination, it may bounce off of one layer and bounce again and reach the destination, but it may also bounce off of another layer and reach the destination. What that means is that you have that same signal arriving at the destination from multiple paths. We talked about that in the last class. So that could also affect how well the receiver or the person receiving that signal hears you. Those signals coming in via multiple means may cause some sort of distortion of the signal that sort of multipart that you have existing may cause fading. So you may hear the signal from one part and then that signal may disappear and it comes through the other part. And the other part may be a lower signal than the other part. And therefore you sense a variation of that signal. And you say, but wait a minute, I'm expressing fading of that signal. You will hear the signal loud 1 minute, and then you will hear it softer another minute. And you say, but wait, that signal is fading. And what could be responsible for that is the multiple path that the propagation of that radio wave takes to get to the destination. Another concept that we need to be mindful of is an antenna that is called a half-wave dipole. So this is our feed line or transmission line or coax as we call it, going from our radio transmitter to the antenna. So this is one leg of the antenna here. And this, sorry about that. And this is the other leg of the antenna here, right? So this is a half-wave dipole, one leg of the antenna, the other leg of the antenna. And we need to be aware that with this half-wave dipole, the signal is strongest broadside to the antenna. So where you have the elements up and down, the signal is stronger broadside in this way as well as in this direction. And this is a graph here that shows us the signal strength emanating for a half-wave dipole. This is the dipole here, and the signal is broadside to the antenna. Notice that the signal doesn't go in this direction so much. It is strongest broadside. So when we talk about a half-wave dipole, the signal is strongest broadside. All right, we will also encounter questions in the question pool asking us to calculate the length of an antenna. So let's go straight through some calculations. So when we go to the question pool, we would have done the calculation already. So a question will ask you, what is the half wavelength? If you have a 6-meter band dipole, right? How long is a half-wave 6-meter band dipole antenna? That's the question that they will ask you. So the key words is half-wave, and the band is 6 meters. So if we were to look at what is half of 6, that is 3 meters. Now, it's kind of funny, yeah? You know, it's an American exam, so they're still in the imperial units, but they have to use scientific SI units as well. So that they will talk about the 3-meter band, but they will tell you that the antenna is so and so inches. So we have to now convert from meters to inches. So if we are looking at a 6-meter band dipole antenna, and it's a half-wave antenna we're looking at, half of 6 is 3, but we need to convert 3 meters to inches. To convert meters to inches, you multiply by 39.4. So 3 meters by 39.4 is equal to 118.2 inches. But that is not the length of the antenna. You have to take off 5% of an antenna's length to calculate the length, right? So that is part of the theory as well. Even though this is the theoretical length, for your antenna to be resonant or for your antenna to work on the band, you have to snip off 5%. So what you have to do is take 5% of whatever length you calculate, remove it, and you end up with the answer. So what we do is we take 95% of the total length, 118.2, and we end up with 112 inches. Similarly, if we are looking at a 2-meter antenna, but they tell us this time it's a quarter wavelength antenna, all right? Quarter wavelength of a 2-meter band antenna. So quarter of 2 is a half or 0.5, right? So we're dealing with 0.5 meters. But again, it's an American exam, so we have to end up with inches. So to convert from meters to inches, we multiply by 39.4. So we take the 0.5 meters multiplied by 39.4. So here we have it. 0.5 meters multiplied by 39.4 inches, we get 19.7 inches. But guess what? That is not the correct answer. What do we need to do? We need to shorten the length by 5%. So to shorten, we take off 5% or we go with 95%, 0.95 multiplied by 19.7, we end up with approximately 19 inches. And these are actually 2 real questions on the question pool. So we're doing it here on the slide deck so that you'll see the calculation. You could always come back to it. when we go to the question in the question pool, you'll see a question, you'll see an answer. We like to work things out here. How do we come to it? There is a bit of information on the question pool, but we're doing it, the workings. So let's see if we could just progress a little further before we take a short break. All right, so another concept is that you can shorten an antenna by using a coil. All right, so you will see that in a question coming up in a little bit. So notice the coil and the antenna here. By using this coil, the total length of the antenna in terms of length from top to bottom is less. What you're doing is really, you have a longer electrical wavelength, but you're physically shortening the length of the antenna. Also, this is what a beam antenna looks like. It's a directional antenna. You have 3 elements here. And the radiation pattern, when you transmit using this antenna, the signal goes in that direction of the arrow. And the signal is stronger in this direction. Because it's a beam antenna, we say that this antenna has gain because it is seemingly causing the signal in this direction to be stronger than had it just been a single element or a dipole. We add on these elements here, an element at the back and an element at the front, and that gives it direction, and it's called a beam antenna. Another concept that we need to be aware of is the concept of radiation angle. So you will see questions in the question pool that tells you, well, if you're using a quarter wavelength antenna, a half wavelength antenna, or a 5/8 wavelength antenna, which one goes further and which one has a higher radiation angle? So quarter is 0.25, half is 0.5, and 5/8 is 0.625, right? So if we look at the radiation pattern of a quarter wavelength antenna, right, which is in blue here, notice that the radiation angle is high, but the antenna signal doesn't go too far, it just goes right here. But notice a half wavelength antenna, the radiation pattern, the radiation angle is lower, but the signal goes a little further. And a 5/8 wave, notice the radiation angle is even lower and it goes even further. So you need to be aware of this relationship between the radiation angle and distance that the antenna will carry the signal or send the signal. So folks, let us take a 2-minute break and take a stretch, have some water, bathroom break, and we'll come back and continue with the questions in the question pool. Okay, welcome back everyone. So before we get into the pool questions, just to address a question asked by Andrew. So Andrew, the reason it's labeled as power, it shows, think of it as signal strength or the amount of signal reaching. It's the concept of gain. It appears as though more power is radiated from the antenna. So that's why they have power, but you could also think of it as that power allowing the signal to go a further distance, right? So there's a relationship in the square law in terms of how far a signal will go based on the amount of power. So that's the reason why they would have said power level, but they didn't give a unit of it at all. They just simply said power level. But I described it in the sense of distance, how far the signal will go, and I'm using a lot of analogies in the course for us to understand. But very good observation, and thank you for the yes, Andrew. Fine, no problem, glad to help. All right, folks, so let's continue with our no-nonsense guide, and we are on page 28, at the bottom of page 28 on the PDF, which is also the page 33 of the PDF itself, all right? So again, we are using the no-nonsense guide. So let's go straight into the questions in the question pool because we dealt with the theory, all right? What property of a radio wave is used to describe its polarization? So remember when we had the diagram with the antennas, we said it's the electric field. So that is the answer. That's the answer to the question, the orientation of the electric field. So once you hear polarization, think electric field. Next question. What can happen if the antenna at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? Remember when we showed you that situation where you had a vertical and a horizontal, and we said that most of the signal you probably will hear a weak signal because the polarization is different. So that's the answer. Signals could be significantly weaker. We talked about this point. They said that with a repeater, the antenna on the repeater uses vertical polarization more often than not. So they make the point here, when you're using a handheld transceiver, make sure to hold it so that your antenna is vertically oriented. Remember we talked about that during the slides. We said people sometimes use a handheld radio like a cell phone at an angle, almost horizontal. Well, what you have just done when you do that, you have wasted most of your signal leaving your antenna because your antenna in your hand, your radio in your hand is horizontal, therefore the antenna is horizontally polarized. But you're trying to reach a repeater antenna that is vertical. You have just wasted most of your signal. So the comment that they're making is make sure you hold it vertically. It takes practice, but it is best practice. So this is something you need to learn. The question is, what antenna polarization is normally used for long distance weak signal CW, which means continuous wave, or think of it as Morse code, and SSB, which is single sideband contacts using the VHF and UHF band. The antenna polarization that is normally used is horizontal. But the reason that horizontal is used is because of the size of those antennas. It makes it easier to mount it horizontally than vertically. So that's the point that they make here next. The reason for that is that weak signal operators are often using what are called beam antennas, and it's much easier to mount and operate beam antennas horizontally than it is to mount them vertically. All right, so just bear that in mind. All right, so they tell us here about sporadic E. We talked about that in the slide deck. So let's go straight to the question pool question. They're asking us which of the following propagation types is most commonly associated with occasional strong over the horizon signals in the 10, 6, and 2 meter band. So they're really talking mostly about the VHF part of the band here, right? Technically 10, meter is not VHF. It's kind of, you know, HF, but, you know, it's close enough to the VHF band to have similar properties. But the point is they're asking about the VHF part of the spectrum, and you have occasional strong. So that means it is fluttering, it's coming and going, right? And we said when that happens, it's called sporadic, but what layer in the ionosphere is used for that propagation? It's the E layer. So therefore, it is the sporadic E. Again, refer back to the slide deck for a visual on this. They also tell us that there are other types of propagations that's used to communicate: auroral reflection, meteor scatter, tropospheric scatter, and tropospheric ducting. Well, we dealt with those theoretically in the slide deck. So let's go straight to the questions in the question pool. What is the characteristic of a VHF signal received via auroral reflection? If you have ever had the opportunity to see it, you'll realize that the lights flash and come and go, and they get bright and dim and they move. They seem to shift all the time, right? So what kind of signal would you expect if you are bouncing your radio signals off of such a phenomenon? The answer is the signal exhibit rapid fluctuations of strength and often sound distorted. Again, auroras are moving, they look moving, they shift, they get bright, they get dimmer, 1 minute they're there and they're shifting. So if you're bouncing a signal off of it, that is what you'll get, rapid fluctuations of strength, and as a result of that, it might sound distorted. Again, hams like to bounce off of meteor showers when you have meteors coming through into the atmosphere. Well, we bounce our radio signals off of them, we point our antenna to it and say, let's try to communicate with another part of the globe. That's called meteor scatter, right? Again, in our slide deck, we looked at it. You need to learn this. What band is best suited when you're using meteor scatter? The answer is the 6 meter band. All right, so you need to simply learn that. What band is best for meteor scatter? 6 meter band. All right, so we dealt with this about whether or not weather affects radio propagation. So they say the short answer is no, but the exception to the rule is tropospheric ducting or tropospheric scatter. All right, so remember we said that we could take advantage of the temperature inversions in the atmosphere, right? So let's look at the question and the question pool associated with it, seeing that we dealt with the theory during the slide deck. What mode is responsible for allowing over the horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? All right, so what allows for that is the tropospheric scatter. Next question in the question pool, what causes tropospheric ducting? Remember we said that you have warm air, cold air, and that temperature inversion is what causes the tropospheric scatter and tropospheric ducting. Well, the answer is temperature inversions in the atmosphere. All right. Okay, another exception to the rule, this is whether weather affects radio transmissions. Remember we said at microwave frequencies, rain does and can affect your signals. So they simply say here that precipitation, and that's a very big word to say rain or snow, that sort of thing, right? That's what precipitation is. Precipitation especially affects microwave signals, especially at frequencies above 11 gigahertz, right? So you need to be aware of that. It's also called rain fade. But notice the frequencies that they're talking about, right? The microwave region. And remember we said microwave is anything above 1 gigahertz, but they say especially above 11 gigahertz, right? So that's why the slide that we have, you will look at it, you will see some lines demarking 11 gigahertz and so on. Question in the question pool. What weather condition would decrease range at microwave frequencies? The answer is rainfall or snow, which is categorized as precipitation. So notice the key words here: weather Decreased range, microwave frequencies. All right. Continuing. Notice they say at lower frequencies, rainfall or precipitation, snow and so on has little or no effect. Question in the question pool. How might fog and light rain affect radio range on the 10 meter and 6 meter bands? Well, the answer is it will have little or no effect. So they didn't say in the microwave part of the band, right? They said 10 meter and 6 meter. Right, so 10 meter is sort of HF, close to VHF, and 6 meter is certainly VHF. So we have been talking quite a lot about the ionosphere and the fact that hams love to bounce signals off of things like the ionosphere. And we utilize HF frequencies when we are bouncing signals off of the ionosphere. Right? So we need to be aware that it's the ionosphere that allows signals to reach very far distances because we bounce signals off of it. But what creates the ionosphere? We had looked at some slides before that show that it's the sun or solar radiation that creates the ionosphere. And there are the D, E, and F layers, with the D layer being the lowest and the F layer being the highest. Question: which part of the atmosphere enables propagation of radio signals around the world? Again, we are very familiar with that. We are bouncing signals off of it all of the time. It's the ionosphere. Which of the following is an advantage of HF versus VHF and higher frequencies? Well, remember we said that we use HF frequencies to bounce off the ionosphere. We cannot do that with VHF and UHF and so on. They go through the ionosphere, but we bounce HF signals, they refract off of the ionosphere. The answer is long distance ionospheric propagation is far more common on HF. All right, so HF is what we typically will use to bounce signals off of the ionosphere. Remember, HF is what? Between 3 and 30 megahertz. We mentioned this sunspot cycle being an 11-year cycle. All right, and also that the number of sunspots, when it increases, can help with HF propagation, all right? So sunspots helps with radio wave propagation. That's the point that we need to take away from this discussion. Let's go to the question in the question pool. Which of the following bands may provide long distance communications during the peak of the sunspot cycle? All right? So the 10-meter band is HF and the 6-meter band is VHF, but it is the low part of the VHF band. So you need to learn that the 6-meter or the 10-meter bands, when you have high sunspot activity or the peak of the sunspot cycle, you may have long distance communications on these bands. When you don't have many sunspots, you do not generally get much communications on these bands. So we need to be aware of that. Again, another diagram we looked at, we saw that the ionosphere during the day is different to during the night. So the frequencies that propagate or transmit or are able to bounce off of the ionosphere during the day and the night is different. So they are telling us here that the frequency bands during the day propagate very well, and during the night, the lower frequencies propagate well. So remember that chart that we looked at? We saw the frequencies that propagate or are able to travel very well at night versus the frequencies that travel well, very well during the daytime. All right? So the question in the question pool is, what is generally the best time for long distance 10-meter band propagation via the F layer? All right. So the answer is from dawn, which is very early in the morning, to shortly after sunset during periods of high sunspot activity. So of course, what we're talking about is daytime, right? So this period here is daytime. They just put it in a very sophisticated way from dawn to shortly after sunset. But we know that is daytime transmission, right? So we know that during the day, propagation is great on the high frequency bands, right? So they ask us about the 10-meter band. So notice that the 10-meter band is good for the daytime, not so good for the nighttime. So that's why the answer is for the 10-meter band, daytime. So all this here that they put is saying daytime. Okay, so this question in the question pool relates to one of the diagrams we looked at earlier. Remember we saw where the signals will bounce off the ionosphere and arrive via different paths? Which of the following is a likely cause of irregular fading of signals received by ionospheric reflection? And the answer is because there's a combining of signals arriving via different paths. That is what causes that fading. The random combining of signals arriving via different paths at the destination is what will cause the signal sometimes to sound distorted or to come and go. And they make the point that this is similar to the other concept we looked at previous class, multipath distortion that occurs on VHF and UHF. But the difference is that this, in the case of HF, the signals are bouncing off of the ionosphere. And they note that the ionosphere is constantly changing. Remember, the sun's rays are moving relative, right? The earth is rotating on its axis. So therefore, the part of the earth that is exposed to the sun is constantly changing, and therefore the ionosphere, the ionosphere of itself is constantly changing because of the amount of sunlight that it is receiving. All right. Let's go to this point here. They make the point that antenna polarization is not very important when we are looking at the HF bands, but it is very important when we are on the VHF, UHF bands. The reason for that is because when we use the ionosphere and we bounce the signal off of the ionosphere and it goes to the earth, it is neither horizontally or vertically polarized. It becomes elliptically polarized, right? So that's why they're making the point that it's not very important, all right? So you could use either horizontal or vertically polarized antennas. So let's go to the question in the question pool. Which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? All right, so again, let's say that again. Which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? The answer they give us, either vertically or horizontally polarized antennas may be used for transmission or reception. Again, because when you send the signal to the ionosphere, it comes back elliptically polarized. So therefore, either horizontal or vertical polarization antennas can be used. If it were that when you send a vertical signal and it bounced off the ionosphere, it came back vertical, well, then you would have had to use a vertical antenna. Or if you had used a horizontal antenna and it bounced off the ionosphere and it came back horizontal, then you should have used a horizontal antenna. But the point that they're making here is that once you are bouncing a signal off of the ionosphere, whether you use a horizontal antenna or horizontally polarized antenna or a vertically polarized antenna, it will end up elliptically polarized, sort of in between horizontal and vertical, if you want to look at it that way. So whichever you use at the receiving end will work, horizontal or vertical. All right. So in the time that we have left, let us go straight into the next item on the curriculum that talks about antennas and feed lines. All right. So we'll go straight into the question pool. Which of the following describes a simple dipole oriented parallel to the Earth's surface? So remember, if it is vertical, right, you have vertical polarization, but if it is parallel to the Earth's surface, you have horizontal polarization. Remember the diagram we looked at? So they're asking us which of the following describes a simple dipole oriented parallel to the Earth's surface, not vertical, parallel. So if it's parallel, then the antenna is horizontally polarized. If they told us that the antenna was at 90 degrees to the Earth's surface, or vertical or perpendicular, those are the other terms that they could use, then it would have been vertical polarization. But they're saying that the antenna is parallel or flat to the Earth, and therefore that is a horizontal polarization. You could think of it when you're sleeping on a bed, you're lying flat, you're parallel to the Earth's surface, you're parallel to the bed, and you are therefore horizontal. Okay, a question in the question pool related to a slide in the slide deck where we showed a half-wave dipole and where the signal radiates. So the question asks, in which direction does a half-wave dipole antenna radiate the strongest signal? If you recall from the diagram, we saw that in a half-wave dipole, the signal is strongest broadside to the antenna. All right, so if you need to review that, you can look back at the slides when you get it, and you will see for a half-wave dipole that the signal is strongest broadside. All right. Remember we did some calculations on the slide deck? Well, this was the question. What is the approximate length in inches of a half wavelength 6-meter dipole antenna? So remember we said we looked at a half wave dipole or half wave antenna that was for the 6-meter band, and we did a calculation. We ended up with the answer 112. All right, so you can on your own look back at that calculation or read up this section here as to how it's calculated, right? All right. So remember we have a relationship between frequency and wavelength. Question is, how do you change a dipole antenna to make it resonant on a higher frequency? So remember the relationship, we said the higher the frequency, the shorter the wavelength. So the answer is, if you want to make it resonant on a higher frequency, you want to make sure that it's compatible with a higher frequency usage. Because higher frequency means shorter wavelength, you have to shorten the antenna or you have to cut it. They say here that if you wanted to make it resonant on a lower frequency, you have to lengthen the antenna. Let's just mention what they talk about here. They say the final length will be affected by the height at which you put the antenna, meaning above the ground or above the house or above the building, as well as any nearby trees or building. So you need to be aware of that those objects around could affect the length of the antenna that you need for a particular frequency. All right. Okay, so the other type of antenna that we talk about in amateur radio is the quarter wavelength antenna. So remember we looked at the radiation angle between a quarter wavelength, a half wavelength, and a 5/8 wave. So we have the quarter wave antenna, and we go straight to the question in the question pool. We did this calculation in the slide deck. What is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? All right, so the calculation that we did, we know that the 146 megahertz is in the 2-meter band. And we did the calculation in the slide deck, which is the same calculation that's shown here. The answer is 19 inches. Again, If you wish, you can go back over the slide deck where we put the calculation a little more methodical, right? But it's the same calculation here. All right, let's see if we could just do a couple more questions in the question pool, seeing that we dealt with the theory in the slide deck. They say that HF antennas can be very long, right? Remember, at those low frequencies, the wavelengths are very long in meters. So to shorten them, we use a technique called loading. And to load, we can either use inductors, remember inductors are coils, or capacitors. But most commonly, we use inductors or coils. Remember the antenna that we showed? We said that it is shorter because they have a coil in it, right? Which of the following describes a type of antenna loading? And the answer is that we have inserted an inductor into the radiating portion of the antenna to make it electrically longer, but it's physically shorter. Physically shorter, but it appears electrically longer. So the inductor is what allows you to shorten an antenna or to load it. Amateurs also use directional antennas or beam antennas. So in this slide deck, we showed what a beam antenna was. We had a dipole, then we had elements at the back and the front, and that caused the antenna to exhibit directional properties and send the signal stronger in one direction. And that is said to have antenna gain when we do that in the direction. We also call those antennas beam antennas. Questions in the question pool. What is a beam antenna? Beam antenna is an antenna that concentrates signal in one direction. It doesn't mean, by the way, that the signal only goes in that direction. It's just that it's the strongest in that direction. So bear that in mind. You still do have some signal going to the back and a little bit off the side and so on, but it doesn't get very far. All right. So we need to learn this, and for the next slide deck, I'll probably show examples of what these look like. But the question in the question pool is, what type of antennas are quad, Yagi, and dish? So I'll show you what those look like for the next class, but we need to know that those are directional antennas. When you hear about a quad antenna or a Yagi is another term that describes a beam antenna. The beam antenna that we saw with the three elements, where the signal was going in the forward direction very strong, that is also called a Yagi. And we should already be familiar with dishes, you know, DirecTV dishes. Those are highly directional antennas because we want to get signal from a satellite in the sky. So we use a dish. We don't want to get a signal from behind us down the road, left, right, and center. We want to point it up and get it directly from the satellite. That's a dish. So quads, Yagis, and dishes are directional antennas. And we talked about the concept of gain. So what is the gain of an antenna? And we will end with this question. The answer is the gain of an antenna is the increase in signal strength in a specified direction compared to a reference antenna. So once you hear about antenna gain, that means you have constructed the antenna in such a way to send the signal strength in one direction stronger as opposed to any other direction. So a beam antenna, for instance, exhibits gain because we have put elements to it to direct the signal in one particular direction. All right. So, folks, our next class will be held on Friday, the 17th of July. I would certainly like to thank everyone for being part of today's class. You have made it thus far. I would like to congratulate everyone for sticking to it. We know it's an effort that you are making, and we certainly do appreciate you being part of this class. Feel free to send us email if you have any questions that you would like to have answered, and we will endeavor our best to answer these questions during our next session. We'll try to prepare those answers for you. Also, feel free to read ahead, and we would strongly suggest that you consider doing some of the questions in the question pool. All right. I think I'm seeing some questions here. Let's just see. Okay, sorry, I thought I saw some questions being raised. All right. So please try your hand at some of the practice exams. Our first session, there are links to those practice exams. And I just want to encourage everyone to try your hand at it, see how you're doing. You may be very surprised as to how many you get correct in even at this stage, even though we haven't yet completed the course, so that you can get a feel for what the exams are like. As a matter of fact, when you do a question in the practice exam that you haven't touched yet, you might be able to take a guess and see if you got it right. And when we actually come to the material, you would have already been familiar with that question. So when we talk about the theory, you can make a bit of a link to, oh, that is what they were asking us, all right? So let me just see if there are any notes. Okay, I'm not seeing anything in the chat. Yes, Carlton, welcome. Thank you very much. Yes, thanks for the comments. All right, folks. So please do have a safe weekend. Do enjoy, and looking forward to seeing you at our next session. So thank you very much, everyone. Do have a good night.